Welcome to Tomorrow Unveiled, where we take the latest breakthroughs and boil them down into clear, actionable, and fascinating insights for you. This week, we are looking far beyond Earth. We're focusing on what seems to be the most important strategic shift happening in space right now. It's this pivot away from, purely government-led exploration towards the messy, difficult, but really necessary work of building a new economy, the orbital economy.
Yeah, that's absolutely the core theme our dedicated research team zeroed in on this week.
Hmm.
For decades, space was all about what can we discover out there.
Right.
But now the focus is shifting. It's becoming what can we actually build and how can we make it last.
Hmm.
We're really witnessing the foundational construction, the scaffolding going up for a commercially viable, sustained infrastructure beyond the Kármán line. This feels like the ultimate maturation point for the whole new space industry.
So we're not just talking about like the occasional science mission or a cool flyby picture. This is different. This is about setting up permanent factories, gas stations, repair shops, actual logistical hubs up there in orbit, treating space like a real industrial frontier.
Exactly. It requires thinking about space not just as a place you visit, but as a place where you operate a business, a sustainable one.
Which makes sense. I mean, if you want a self-sustaining human presence off-world, you can't stay tethered forever to Earth's supply chain, right? It's just too expensive, too slow.
Precisely. You hit the nail on the head. The engineering challenges, the market maturation needed, it's all incredibly demanding, no question. But the breakthroughs highlighted by the research team just this past week, they show we're actually starting to cross some key technological and economic thresholds. It's happening.
Okay. So our mission today, here on Tomorrow Unveiled, is to really dig into the four interconnected pillars that our research team identified as the most critical, the most corroborated breakthroughs from the last 7 days. Think of them like the four legs of the orbital economy stool. They all need to be strong. First, in-space manufacturing, or ISM. Is it finally reaching industrial maturity? Second, next-gen propulsion and launch reliability. The evolving logistics backbone needed to get stuff up there and move it around. Third pillar, the critical race, and it really is a race, for on-orbit servicing OS standardization, making repairs and refueling routine. And finally, pillar 4, laying the groundwork for Cis-Lunar Logistics, basically making the moon the next supply hub in this whole system.
And these four areas, they're completely intertwined, aren't they? You can't really have one without the others working well. I mean, making stuff in orbit is kind of pointless without cheap, reliable launch to get the raw materials and the factory itself up there. And then that infrastructure, once it's built, it has to be maintained, serviced. And only once you nail those first three can you realistically start thinking about expanding into the cislunar domain out towards the moon.
Okay, let's unpack this then. We're going to start with pillar 1, the in-space industrial revolution. We're talking about moving the factory floor off-world. And the biggest news this week wasn't just another little prototype, was it? It sounds like it was the validation of making actual industrial-grade hardware in microgravity, for real this time.
That's exactly right. The biggest headline here really shifts orbital manufacturing out of the realm of, let's say, plastic trinkets or simple prototypes, and firmly into industrial-grade hardware. This is the landmark achievement by the European Space Agency, ESA, working closely with Airbus. They successfully and safely operated a metal 3D printer aboard the International Space Station, the ISS.
Now, that sounds simple when you say it like that, but it feels like a massive leap technologically speaking. Because previous 3D printing in orbit, it was mostly polymer-based, right? Good for making, I don't know, a wrench or a small bracket maybe. But this new capability means actually fabricating robust, load-bearing metallic components, using stainless steel wire as the feedstock. The material is the key difference here.
Absolutely. And think about the engineering hurdle involved. Just pause on that for a second.
Yeah.
We are talking about using a high-power laser, operating at temperatures exceeding 1,200 degrees Celsius. That's comparable to a major industrial welding operation. And you're doing it safely inside a pressurized tin can, basically, full of astronauts and really expensive life-critical electronics.
Wow. Yeah, I can just imagine the thermal management alone must be an absolute nightmare. How did the engineers manage to safely control that kind of intense heat and the whole process within the closed-loop atmosphere of the ISS? That seems incredibly risky.
Well, the safety architecture they designed is, frankly, an engineering marvel in itself. The printer isn't just sitting out in the open. It's housed inside this triple-redundant, hermetically sealed box. And it's not just a simple casing. It's like a microenvironment within the station. The internal atmosphere is meticulously controlled. Oxygen levels are kept really low to minimize any combustion risk, obviously. And that sealed box is critical for preventing any fumes or, crucially, tiny metal particulates from escaping and contaminating the station's very delicate air filters and life support systems. The whole system is designed around functional safety standards that honestly far exceed what you typically see in a terrestrial factory.
And the research team really highlighted the specific manufacturing method they chose using wire-fed additive manufacturing instead of powder-based systems. Could you explain for our audience why that choice, wire over powder, is so deliberate and so critical when you're working in microgravity?
Yeah, it really comes down to kinetic control, or rather, the lack of it in zero-G. If you were trying to use a powder-based system, which is actually pretty common for metal 3D printing here on Earth, well, you run a huge risk. That metallic powder feedstock could just float uncontrollably if even the slightest seal failed or the containment system had a glitch. And that powder, if the crew inhaled it, or if it got into electronics and caused a short circuit, I mean, it would be catastrophic, just unthinkable. The wire feedstock, though, it gives you what we call positive feed control. It's a solid strand of metal right up until the laser melts the precise tiny point needed for deposition. It just makes the whole process far more manageable, much more reliable, and inherently safer in a microgravity environment.
Okay, so this really shifts the whole narrative then. It's moving from let's test if we can print anything in space to, okay, we've now validated the concept of an orbital factory floor for real parts. What's the ultimate strategic payoff for de-risking metal manufacturing like this? Where does this lead?
The significance is, well, it's foundational, particularly for long-duration human spaceflight. Think about the Artemis program's lunar gateway or eventual missions to Mars. When you're months, potentially years away from Earth, resupplying critical spare parts becomes logistically impossible, or at least prohibitively expensive and slow. So the ability to print robust, certified metal components on demand, whether that's custom repair tools the crew needs, or replacement parts for essential systems like propulsion, maybe even structural elements for habitat expansion, it enables true crew self-sufficiency. It fundamentally changes the logistics equation and dramatically reduces the risk profile of those deep space missions. It's really all about resilience.
Okay, so that's building the strong stuff. Let's shift gears slightly. From structural integrity now to microscopic precision. The next big piece of news our research team flagged in space manufacturing involves the semiconductor frontier, targeting maybe the highest value product imaginable. Tell us about this collaboration between Axiom Space and Resonec. What are they trying to do?
Right, this partnership is different. It's a pure commercial play. They're aiming squarely at producing high-performance semiconductors and other advanced materials right there in orbit. They aren't printing wrenches or brackets. They're attempting to grow perfect crystals for the next generation of microchips.
But we grow crystals for chips on Earth all the time, don't we?
Yeah.
Why does microgravity suddenly become the ideal place, or maybe even the necessary place, to manufacture these crystalline structures that are the absolute backbone of modern electronics?
It comes down to tackling a fundamental physical limitation imposed by gravity itself. It sounds simple, but it's profound. When you grow large silicon crystals here on Earth, even under the most controlled conditions, the temperature differences within the liquid melt tank inevitably cause gravity-induced phenomena. You get convection currents stirring the melt, and you get sedimentation, tiny particles settling out. These forces, driven purely by gravity, introduce minute, essentially unavoidable defects into the crystal lattice structure as it grows. And even tiny defects limit the ultimate performance of the chip. They decrease the yield, the number of usable processes you get from each wafer, and they reduce the overall capacity of the material itself.
Okay. And in orbit, without gravity messing things up, those distortions just vanish.
Exactly. In microgravity, the melt remains perfectly still, perfectly uniform. There's no up or down for hotter, less dense material to rise or cooler, denser material to sink. This unique environment creates the pristine conditions needed to potentially grow larger, more uniform, and virtually defect-free crystals. And this isn't just about making today's chip slightly better. The real hypothesis, the big potential win, is that microgravity might enable entirely new classes of materials, complex compounds and alloys that are physically impossible to fabricate terrestrially with the required level of purity.
Wow. Okay, that moves well beyond just simple efficiency gains then. That sounds like it could become a major economic and, frankly, strategic imperative, especially when you think about all the recent geopolitical turmoil and vulnerability surrounding semiconductor supply chains here on Earth.
It absolutely is. From a national strategy perspective, this is a very concrete, commercially driven initiative that directly tackles that geopolitical vulnerability.
Right.
By developing the capability to manufacture these critical high-value components in orbit, you're essentially reshoring critical infrastructure, but not to another country. You're reshoring it to a neutral, technologically superior domain space. It completely reframes low Earth orbit, doesn't it? From just a place for science experiments to a high-value strategic industrial zone.
So the speed of development on this orbital factory floor is clearly picking up pace. But the third major ISM breakthrough our research team flagged involves dramatically shortening the design cycle itself. Using artificial intelligence, we saw news involving Northrop Grumman, Luminary Cloud, and NVIDIA. What's happening there?
Yeah, this collaboration is focused on developing something they're calling a physics AI foundation model. And the goal here is truly revolutionary speed and iteration in the design process. They are claiming, and it's a bold claim, that this technology can design highly complex components, like, say, spacecraft thruster nozzles, in a matter of seconds.
Seconds. That sounds insane. I mean, traditionally, designing and validating a critical aerospace component like a thruster nozzle involves months, maybe even years, right?
Yeah.
You've got rigorous finite element analysis, computational fluid dynamics, CFD simulations, countless iterations by highly specialized human engineers. Plus, you have the huge hurdle of meeting incredibly strict functional safety standards, things like AS9100 or ESA certification. How can AI do that in seconds?
Well, the speed is definitely the headline grabber, but
Hmm.
the mechanism behind it is what's really interesting. This physics AI uses pre-trained models. It's been fed vast amounts of data based on the fundamental laws of physics, plus extensive experimental results from real-world tests. So it can rapidly generate, simulate, and predict the performance of incredibly detailed designs almost instantly. It essentially leapfrogs those initial, very time-consuming simulation loops that engineers traditionally have to go through.
Hmm.
The claim isn't just seconds for a single design iteration, but that this approach dramatically shortens the overall design-to-test cycle time for certain components down to potentially just 3 months.
Okay, but doesn't that inherently introduce a huge element of risk? Aerospace is built on rigor, on slow, methodical iteration for safety. If the AI is spitting out designs that fast, how do we actually trust the functional safety of the component without human eyes, without decades of institutional knowledge signing off on every detail?
That's the crucial point, and it's an ongoing tension, absolutely. The human engineer doesn't just disappear from the process. Their role changes. They become more like the curators of the input data, the definers of the operational constraints and the safety requirements. The AI is like a massively parallel processor for exploring the design space. It allows the engineers to gain huge amounts of time back, which they can then spend on final optimization, on more extensive physical testing, on exploring edge cases before anything gets manufactured. It might mean they can physically test 10 promising prototype variations instead of just one or two, and those prototypes are inherently much closer to the optimal design right from day one, thanks to the AI's initial heavy lifting.
Hmm. So the comparison our research team made, likening this shift to the introduction of computer-aided design, CAD, decades ago, that feels pretty apt then.
I think it's a very good analogy. It feels like a true paradigm shift. CAD took the physical drawing board and digitized it, right? Making iteration much easier and faster.
Hmm.
Physics AI seems poised to take the entire iterative design process, the simulation, the material science considerations, the geometry optimization, and automate large chunks of the initial exploratory phase. This fundamentally transforms the potential speed of iteration and innovation in the aerospace industry. And it strongly implies, doesn't it, that the next generation of spacecraft might be designed less by traditional mechanical engineers starting from a blank sheet, and perhaps more by programmers and material scientists who are experts at feeding the AI the right physical parameters and constraints. It's a fascinating shift in required skills.
Okay, so we've established the orbital factory floor is becoming viable. It's accelerating rapidly thanks to things like AI. But manufacturing is only half the battle, isn't it? We need reliable ways to get things to the factory and efficient ways for those things to move around once they arrive. Logistics.
Exactly. And that leads us directly into Pillar 2, the evolving logistics backbone. This whole section, based on the research team's findings, really focuses on driving efficiency and, interestingly, a healthy dose of pragmatism in how we move mass around and maneuver assets in space.
And we saw some significant movement in the propulsion sector this week, particularly that consolidation news Voyager Technologies acquiring Exoterra systems. That sounds like it strengthens the domestic U.S. capacity for flight-proven electric propulsion technologies, right? Now, for many listeners, they hear rocket and they just picture massive chemical explosions, fire, and smoke. Can you give us a quick ion thruster primer? What are they and why are they so vital for this orbital economy idea?
Sure. Ion thrusters are kind of like the tortoises of the space propulsion world. They're incredibly slow off the starting line, but they always win the endurance race. Essentially, they use electricity, usually generated by large solar panels, to ionize a propellant gas. That could be xenon, argon, sometimes even iodine now. Then they use electrostatic grids or magnetic fields to accelerate those ions out the back at extremely high velocities. That acceleration creates thrust, Newton's third law.
Okay, so the famous characteristic is that extremely low thrust, right? Almost imperceptible.
Exactly. The thrust from the famed Deep Space One ion thruster, for instance, was often quoted as being roughly equal to the weight of a single sheet of paper resting on your hand. Tiny. But, and this is the crucial but, this incredibly low thrust is coupled with an incredibly high specific impulse. Specific impulse is basically the measure of fuel efficiency for rockets, how much thrust you get per unit of propellant consumed over time. And the efficiency of ion thrusters is orders of magnitude better than traditional chemical propulsion.
Okay, let's break down that trade-off in practical terms for the listener. If the thrust is that low, why wouldn't you just use a punchier chemical thruster for everything?
Well, because that chemical thruster, while powerful, uses up its massive fuel tank in a matter of minutes. It's great for quick, high-energy maneuvers like getting off the ground or making a fast orbital change. But it requires huge amounts of propellant mass. An ion thruster, on the other hand, because its amazing specific impulse, can sustain its gentle acceleration for months, sometimes even years, using only a tiny fraction of the propellant mass. This constant, gentle push allows spacecraft to eventually reach speeds or orbital altitudes that would be completely impractical or uneconomical using chemically limited rockets. So they're exceptionally good for things like sustained orbital maintenance, constantly counteracting atmospheric drag on a space station, for example, or for slowly spiraling satellites up from low Earth orbit to geosynchronous orbit over many months. You basically trade quick maneuvers for massive savings in propellant mass. And that mass saving is absolutely essential for making long missions, say, 10 or 15 years economically viable.
And we're seeing this evolution play out in real time, right? Not just in research labs anymore, but on operational spacecraft across the globe.
Oh, absolutely. It's becoming mainstream for certain applications. China's Tiangong space station, for example, relies on 4 Hall effect thrusters, a type of ion thruster for its routine orbit maintenance, just constantly nudging the station to keep it from dipping too low. We also saw that interesting evolution with SpaceX's Starlink constellation. Their earlier satellites used krypton gas in their Hall effect thrusters, but the research indicates they've since transitioned to using argon for their newer V2 mini satellites. Why? Because argon offers a slightly higher specific impulse, better efficiency. That constant hunt for even fractional efficiency gains is what really drives the economics of the orbital economy. And it's not just noble gases anymore. Iodine has also been successfully demonstrated as a propellant in orbit now by systems like the NPT-30I2 thruster. That's significant because iodine is much more common, cheaper, and easier to store than xenon, potentially opening up electric propulsion to even more missions.
Okay, that focus on fuel efficiency is crucial because even with the most efficient propulsion systems imaginable, maybe the biggest logistical challenge that remains is simply keeping the fuel usable once it's up there, especially the high-energy stuff. And that naturally leads us to the cryogenic fueling problem, doesn't it? The LXAT mission seems to be targeting this specific Achilles heel.
That's right. Rocket Lab just announced they completed the Photon spacecraft build and passed the systems integration review for the LOXSAT mission. This is a partnership with a company called ETA Space under NASA's Tipping Point program, which funds key technology demonstrations. And the problem they're tackling is immense. Cryogenic fuels, like liquid oxygen LOX or liquid hydrogen, are essential for the high-performance chemical engines you need for high-thrust maneuvers, like landing on the moon or departing Earth orbit quickly. But in orbit, these super-cold liquids face constant heat radiating from the sun, from the Earth, even from the spacecraft itself. This causes them to constantly risk vaporization, what we call boil-off, and that boil-off means inevitable loss of precious fuel over time.
So the goal of LOXity is something they're calling zero-loss storage. Walk us through the engineering difficulty there. Is it just a matter of putting like a really good thermos insulation on the tank?
If only it were that simple. It's far more complex than just a super insulated thermos bottle, unfortunately. Remember, in microgravity, liquids behave very strangely. They don't just settle nicely at the bottom of the tank like they do on Earth. They can cling to the walls, form bubbles. It's messy. This makes managing thermal stratification layers of different temperatures within the liquid and predicting heat transfer incredibly difficult. Achieving zero-loss storage involves integrating active cooling systems, like cryocoolers, which act like refrigerators for the fuel, alongside advanced passive thermal controls, like multi-layer insulation and sun shields. Plus, you need sophisticated fluid management techniques to handle any small amount of gas that does get created by boil-off, maybe recondensing it or using it for low-thrust maneuvers. They're essentially testing a whole suite of technologies to condition the propellant and ensure it remains dense and liquid over very long periods, weeks or months, without just venting it away.
And this data, it's not just for a cool science project, is it? Our research team emphasized this is really infrastructure data. What future commercial economy is this feeding into?
This is absolutely fundamental. The data gathered from OLEXSAT is essential input for designing the proposed cryodock that's envisioned as a commercial propellant depot in low Earth orbit, potentially operational by 2030, according to some roadmaps. Think about it. If you can reliably store large quantities of cryogenic fuels in space without loss, you effectively create the indispensable gas station infrastructure. That infrastructure is necessary to make deep space exploration economically viable, and maybe even more importantly, it's crucial for enabling the widespread reusability of large space vehicles, both in Earth orbit and beyond. No more throwing away giant upper stages after one use. And this directly echoes NASA's own plans, doesn't it? Their plan to use similar advanced electric and cryogenic propulsion systems on the Lunar Gateway space station. It all connects.
Okay, so we have increasingly efficient engines, and now a clear path towards storing their fuel in space depots. Let's pivot now to the launch vehicles themselves, the rockets that get everything up there in the first place. Specifically, the maturation that seems to be reflected in that recent Relativity space milestone, their Terran R booster. Successfully completed flight intent hardware testing. Its primary structure withstood over 3.7 million pounds force of tension. That sounds like a major engineering success.
Oh, it absolutely is a phenomenal engineering success on its own merits. Demonstrating that kind of structural integrity is critical. However, the real story here, the one our research team really highlighted is significant for the industry, is the strategic pivot the company has made along the way. Remember, Relativity Space was founded on this really compelling, almost radical dogma of building the world's first fully 3D printed rocket. Everything printed. Now, with the Terran R, they've quite definitively shifted to what they're calling a hybrid approach.
Wait a second. If their entire initial business model, their whole investment narrative, was predicated on the disruptive potential of being fully printed, doesn't this hybrid approach signal, well, if not quite a failure of that original radical concept, then at least a massive concession to market reality? What does this hybrid approach actually mean for the big cost-saving argument that 3D printing was supposed to deliver?
That is the absolute critical question, isn't it? And I wouldn't call it a failure. I think the research analysis suggests it's more like market pragmatism trumping technological or ideological purity. The hybrid model means they continue to use advanced additive manufacturing 3D printing, but strategically, for the really complex performance-critical parts. Things like the intricate internal cooling channels and geometry of their ENR engines, that's where 3D printing truly excels, allowing rapid iteration and creating structures that are simply impossible or too expensive to make using conventional methods.
Okay, so they print the complex bits, but what about the big, simpler parts, like the massive propellant tank barrels and other primary structures?
Yeah, for those large, relatively simple cylindrical structures, they are now openly utilizing more conventional manufacturing methods. Things like welding together large rolled aluminum sections, tried and true techniques. The shift seems to represent a recognition that while 3D printing is incredibly disruptive and enabling for certain complex components, it's maybe not yet economically competitive or perhaps just not fast enough for manufacturing the simplest, largest primary structures when you need to hit a really high production cadence to meet launch goals.
So this feels like a really crucial sign of market maturation in the whole new space sector then. It suggests that actually hitting a reliable launch cadence, delivering a competitive product to customers on time, has become more important than strict adherence to a radical, differentiating technological ideology.
That is precisely the narrative emerging from the analysis. It feels like the moment new space grew up, in a way. It's a necessary, maybe inevitable shift from a purely technology-centric vision, we must 3D print everything because that's our thing, towards more pragmatic, market-driven engineering. We must use the right manufacturing process for the right component to deliver a reliable, competitive rocket quickly. For investors, for future customers looking for dependable launch services, this pivot towards pragmatism arguably signals that reliability and production cadence have now become the ultimate measures of success, maybe even more so than just being the most technologically radical player. And that pragmatic strengthening of the launch sector is, of course, essential for the overall logistics backbone needed to support this orbital economy we're discussing.
Okay, So, with the ability to build factories in space and increasingly pragmatic and efficient logistics to support them, we now enter the final two pillars. These are the ones that ensure this entire complex system can actually be sustainable and scalable in the long run.
It's exactly. Pillar 3 is all about that transition, moving away from the old model of disposable space assets towards truly serviceable, long-lasting infrastructure. It covers standardization, servicing, and absolutely crucially, sustainability. And on-orbit servicing, or OS, is clearly at a fascinating strategic crossroads right now.
Yeah, it seems like we're seeing two very different approaches emerge almost simultaneously.
We are. Our research team identified these two necessary but quite distinct paths for on-orbit servicing that reflect the current mixed state of orbital infrastructure. The first path is what you might call the high-value, high-complexity, bespoke approach. Custom jobs, basically.
Which is perfectly exemplified by that recent news. NASA awarding a $30 million contract to Catalyst Space Technologies. Their mission is to reboost the Swift satellite, right?
That's the perfect example. Swift is a really valuable legacy scientific satellite. It's done amazing astrophysics work, but it was launched years ago, long before anyone was seriously designing satellites for servicing. So it's what we call a non-cooperative target. It has no grapple fixtures, no standardized docking ports, nothing designed for another spacecraft to easily grab onto it. Catalyst is now tasked with developing a completely custom, complex robotic solution to rendezvous with, capture, and gently reboost this aging asset, essentially saving it from orbital decay before maybe 2026. But because the satellite wasn't designed for this, the servicing mission itself has to be custom built from the ground up. That makes it inherently expensive and technologically very complex. NASA here is acting as what's called an anchor customer. They're essentially subsidizing the development of this really high-value, complex capability, partly to save their irreplaceable government asset, but also to help mature the technology for the future.
Okay, so that bespoke path saves critical existing assets, which is important, but it obviously can't scale up to support a whole economy, can it? It's just too expensive, too slow for routine operations. For real growth, you need the second path that the research highlighted, standardization.
This is absolutely the key. It's the key to massive, scalable economic growth in pretty much any large-scale infrastructure development, whether it's on Earth or in space. Think about the global economy here on Earth. It wasn't just revolutionized by slightly better book designs, was it? It was revolutionized by the standardization of the humble shipping container. That changed everything. And we are seeing the very early stages of the space equivalent of that container standardization happening right now. It's highlighted by that strategic partnership announced between ISpace and Orbital.
Right, they're focusing specifically on creating a common refueling interface. It's called the Standardized Interface for Docking and Refueling Payload, or SIDRP. Why is establishing this common refueling interface so strategically important right now, even before the big orbital depots and lunar bases are fully built? It seems a bit early.
Well, it might seem early, but it's actually the perfect time. Because whoever manages to define the standard interface early effectively owns the infrastructure protocol for potentially everyone else who follows. It's a huge first mover advantage.
Yeah.
They're quite explicitly positioning themselves to own the gas pump nozzle protocol, if you will, for the entire international lunar and cislunar community. Just imagine the chaos if every satellite operator, every country, developed their own unique docking and refueling connection point. You'd completely fragment the market. Refueling would become financially prohibitive, logistically a nightmare.
Yeah, the analogy really holds up. Imagine if every make of car on Earth required a completely unique fuel nozzle design and a different payment system at the gas station. It would be unworkable.
Exactly. It would stifle the whole industry. So, by pushing hard now for a common open interface, they're trying to guarantee interoperability from the start. Orbital apparently plans to test this SIDRP interface first in LEO, maybe as early as 2025. Before they integrate it onto a future lunar mission. If they succeed, and if others adopt it, this first-mover advantage could position their protocol as the de facto standard. And that simplifies logistics enormously, drives down costs dramatically, and enables a true ecosystem where potentially anyone can pull up to the future lunar gas station, dock, refuel, and pay, regardless of who built their spacecraft. Standardization is often the unsexy, overlooked engineering detail. But it's the kind of thing that ultimately unleashes trillion-dollar industries.
Okay, so standardization drives the economy, makes it scalable. But sustainability is what protects that economy in the long run. We can't build this amazing orbital economy if we simultaneously allow Kessler syndrome runaway space debris to render critical orbits unusable. What's the current reality check on the debris situation? How bad is it?
The challenge is significant, and it's growing, almost exponentially. The numbers are sobering. Current tracking catalog somewhere around 40,000 objects, large enough to be tracked from the ground. But the real problem is fragmentation events. Things like accidental collisions or old, derelict rocket stages exploding because they still have residual fuel on board. These events create clouds of new, smaller, untrackable debris. The result is that the number of objects in key orbits is actually growing faster than objects naturally re-enter and burn up in the atmosphere. So Kessler syndrome, the nightmare scenario of a runaway chain reaction where debris collisions create even more debris, eventually making certain orbits unusable, is a very real threat, particularly to busy areas like LEO and GEO. If we don't get serious about actively managing this orbital environment, we risk choking off access to these critical regions.
Right. So we need solutions on two fronts, don't we? We need passive solutions, ways to prevent creating new debris in the future, and we need active solutions, ways to clean up the dangerous junk that's already out there. Let's start with the passive prevention methods. What advancements did the research team see this week?
On the passive front, ESA's flight ticket initiative is backing an interesting Spanish mission called PERSE. This mission plans to test something called an electrodynamic tether. The concept itself is fascinating. Imagine deploying a very long, maybe a kilometer-long, thin aluminum tape from a satellite at the end of its operational life. As this conductive tether moves through the Earth's magnetic field, it naturally generates an electrical current, which then interacts with the magnetic field again to create a Lorentz force. This force essentially acts like drag, even in the near vacuum of space.
Yeah, so it's basically a propellant-free deorbit system. It uses physics to bring itself down.
Precisely. It's passive prevention built in. You design this relatively simple, lightweight system into the satellite from the start. When the mission is over, you deploy the tether, and it automatically, although perhaps slowly, increases the drag on the satellite, causing it to deorbit much faster than it would naturally. This ensures responsible end-of-life disposal without requiring the satellite operator to reserve precious, expensive propellant specifically for that final deorbit maneuver. This could be crucial for keeping LEO sustainable, especially with large constellations going up.
Okay, that covers prevention. And what about the flip side? Active solutions for tackling the debris that's already posing a threat up there.
On the active debris removal, or ADR front, Orbital Systems just won a NASA contract. They're developing an autonomous system called RITANS. This looks like a more classic active solution conceptually. It apparently utilizes some kind of net and tether mechanism. The idea is to have an autonomous spacecraft that can rendezvous with specific large pieces of dangerous debris, think defunct upper stages or large satellite fragments, capture them, probably with a net, and then actively pull them down to burn up safely in the atmosphere. Both approaches are vital. Active removal is needed to tackle the immediate threats from the legacy junk already up there, while passive prevention needs to become standard practice for all future satellites to avoid making the problem even worse. We absolutely need both for the long-term health of the orbital environment.
This is really fascinating stuff. If you're finding this insightful, and we hope you are, please take just a moment to like this video if you're on YouTube, subscribe to Tomorrow Unveiled, and maybe consider hitting that new hype button. It really helps us reach more viewers like you. And of course, make sure you turn on notifications so you never miss an update on the future we're exploring.
And if you happen to be listening on a podcast service, maybe Apple Podcasts or Spotify, we'd be incredibly grateful if you could leave us a quick rating and perhaps a review for Tomorrow Unveiled. It genuinely helps new listeners discover the show.
So let's bring it all together. We've broken down these 4 pillars. Orbital factories becoming real, the logistics getting more pragmatic and efficient, the crucial push for standardization and servicing, and the focus on sustainability through debris management. The core narrative that emerges, looking at the research from this week, is that these developments, the metal printing, the AI design speedups, the hybrid rockets, the refueling standardization efforts, the debris removal demos, they aren't happening in isolation. They seem to be creating a powerful, self-reinforcing economic loop.
It really feels like the convergence we've been anticipating for years is starting to happen now. Cheaper, more reliable launch, which is exemplified by that pragmatic engineering shift we saw with Terran-R, that helps fund the deployment of actual infrastructure in orbit. Things like the upcoming private space stations, like VAST's Haven 1. This infrastructure then becomes the host for in-space manufacturing operations, making those high-value products we talked about. And that manufacturing and the infrastructure itself is then made more resilient, more sustainable, through the development of on-orbit servicing capabilities, which are themselves enabled by standardization protocols like SIDRP. Every pillar really does support the others. It's becoming an ecosystem.
And this entire emerging economic ecosystem seems poised to break the traditional bounds of just staying close to Earth in low Earth orbit.
That's the ultimate payoff, isn't it? That's Pillar 4, Cis-Lunar Logistics. It's the next frontier. The development of these new logistical nodes, like the lunar refueling depots being envisioned by companies like iSpace and Orbitate, that's essential infrastructure needed to expand this whole economic sphere out into the cislunar domain, the space between Earth and the Moon. The goal is clearly shifting beyond just LEO utilization. The long-term goal is enabling lunar industrialization, lunar settlement, this convergence of technologies, automated docking becoming routine, in-space manufacturing maturing, efficient orbital logistics chains it's transforming LEO. It's moving from being primarily a government-run laboratory, like the early ISS was, into becoming a true commercial hub. A proving ground, really, for developing and testing the systems we'll eventually need for permanent settlements on the Moon and eventually on Mars.
And we should also probably just briefly acknowledge, as our research team noted, the key international movements that are reinforcing this overall shift this week. It's definitely not just a commercial or purely Western effort anymore.
No, the advancements are genuinely global now, which is actually a very healthy sign for the industry. You had JXA, the Japanese Space Agency, successfully completing the systems integration review for its next-generation HTV-X1 cargo spacecraft. That vehicle will provide significantly enhanced cargo delivery and even power capabilities for the ISS and future stations. And meanwhile, China continues its very clear operational commitment to long-term human presence in orbit. Their Tiangong space station continues to utilize those Hall effect thrusters for routine orbit maintenance, constantly proving out the reliability and efficiency of electric propulsion for very long-duration missions. Everyone is building capability.
So ultimately, the shift feels undeniable, doesn't it? The commercial space sector globally is now focusing really intensely on the how. How do we do the repeatable engineering? How do we build the scalable logistics? How do we implement the standardization required for permanent presence and eventually for profitability in space?
It feels like a critical mass is being reached. The convergence of things like physics, AI driving design, the pragmatic shift by relativity towards hybrid engineering, the race to establish that universal refueling protocol, it all points in the same direction. Space is rapidly transitioning. It's no longer just the domain of scientists primarily focused on discovery. It's increasingly becoming the domain of industrialists, engineers, and entrepreneurs focused on building sustained commerce.
Well, as always, we love hearing your thoughts on all this. Whether you're watching on YouTube or listening on your favorite podcast app, please do leave a comment and let us know what you think about building this self-sustaining economy in space. And maybe a specific question to chew on based on our conversation today. Given this rapid shift we're seeing towards AI-driven design and these more pragmatic hybrid engineering models, does this mean the next truly great aerospace breakthroughs are more likely to come primarily from the traditional mechanical and aerospace engineers? Or could they increasingly come from programmers and material scientists who are becoming expert at feeding the AI the right constraints and data? Think about the implications of that potentially radical shift in the industry's talent base and let us know your perspective. Thank you for tuning in to Tomorrow Unveiled. We'll see you next time.